So last we left, we talked about basically we have two clear solutions. We have the silver nitrate, which is probably here, and then we have the potassium chromate, which is here, and they're both clear. And when you mix them together, the cation and the anions switch partners. So the silver goes with the chromate, and the potassium goes with the nitrate. Potassium nitrate is soluble. Okay, what's insoluble, what that red stuff is actually this right here, the silver chromate. And one of the things I want to emphasize is, we talked about equilibria before, so kind of think of it as that region around, kind of the amniotic fluid around that crazy looking thing, actually that is saturated with the silver chromate. Okay, I hope that makes sense. It's saturated with silver chromate, so some silver chromate comes out. And it's in dynamic equilibrium, so I just think that is so cool. Some solid is dissolving, and some that is dissolved is precipitating out, crystallizing, as my mother would say. So in this sort of problem, we are focusing on the insoluble salt. It's funny because we say it's insoluble, but it's soluble to just a certain, not very much degree, okay? All right. So, what am I going to do now? Oh, yeah. Okay, so let's look closely at this lead 2 chloride, which is relatively insoluble. We could write the KSP expression or the equilibrium constant expression, and it would look like this. The cation and the anion raise their stoichiometric coefficients. And we talked about, so KSP is your solubility product constant. It's your equilibrium constant. That's what KSP is. Q, or QSP, sometimes I'll put it SP since it's for a solubility product. Q, or QSP, is a snapshot. And it's the same thing as our reaction quotient snapshot before. It doesn't have to be at equilibrium. It could be before equilibrium, or it could be after equilibrium, kind of like that. So we're actually, to work these problems coming up, we are going to come up with a Q, or QSP. So for instance, if the Q, or the QSP, is less than the K, or the KSP, then we said that it's too small, so we need to form more products. And more products, down with this lead 2 chloride, more products means more dissolves. More dissolves. So basically, if you have this situation, then more is going to go into solution. More into solution. Now, if it's greater than, if your Q or QSP is greater than your K or KSP, then that means you have too many products, okay? And of course the products are the dissolved form, so if you have too many products, it's actually going to go back this way. And in that case, it's going to precipitate out. So if your Q is greater than your K, or QSP is greater than your KSP, then precipitate will form, or be forming. Bottom line. So snapshot, compare it to your KSP, and you know whether something's going to precipitate or not. So this just kind of restates it. If Q is greater than K, if your snapshot is greater than K, then actually you have too many products. The products are your dissolved cation and anion, so it's going to have to go back to form reactants, which is your solid stuff. Okay. So let's work a problem. Let's pick on lead. Let's pick on lead 2 chloride, just like the equilibrium we looked at. So the KSP for that salt is 1.6 times 10 to the negative 5th. And this is where I think I was going to write a little picture on the board. You got it. You got some of your Chem 1 skills need to be coming in order here. So we are going to add 1.20 grams of NaCl. And hopefully you're like, oh, I know that's soluble. So when we add it to this liquid down here, it is going to dissolve and break up into Na pluses and Cl minuses. The stoichiometry is a 1 to 1 to 1 there. And what we're adding it to is 100 milliliters of 0.012 molar PbNO3, lead 2 nitrate. So hopefully you're okay with this, that this is soluble, lead 2 nitrate. So your lead 2 nitrate has done this. Pb plus 2 plus 2NO3 AQ. All right. So it goes on to say, when you mix this thing, are you going to get a lead 2 chloride precipitate? So bottom line is we need to come up with a Q and compare it to our K, which was given. So the exchange reaction actually looks like this, where we have the two salts, the salt we're adding and the salt that's already in the beaker. They exchange, and you want to be able to write this balanced exchange reaction. But what we're really interested in is the lead 2 chloride. So not only write that exchange reaction with a one-way arrow, but also write the insoluble salt as an equilibrium. And of course, hopefully what comes naturally after that is to write the KSP expression. So KSP is equal to the molar concentration of the lead 2 raised to the first power times the molar concentration of the chloride ion squared. And we know that our Q, or QSP, takes that same form, but it's a snapshot, just to emphasize this. So all we got to do is come up with an ion concentration, the lead 2 ion concentration and the chloride ion concentration, plug it in, and compare it to this. That's all we're going to do. So it's not too bad. So like this slide says, in working a problem like this, you kind of take the scenario of what are the concentrations of the cation and anion of interest before any precipitation begins. All right. So before the chloride ion is added, swimming around down here, we have 0.012 molar lead 2. Now be careful, because this molarity gives, 0.012 molar Pb. But if I were to write down the molarity of the nitrate, you probably would tell me it's 0.024. Yes. So be careful. So that's what we're going to plug in. Now we need to come up with what is the molar concentration of the chloride ion from that 1.20 grams that's added to that 100 mils. So this is a Chem 1 problem. I was looking at this and I decided to kind of break it up. If we put the mass of the sodium chloride, 1.20 grams, over the volume, which is 100 mils, that's probably where I'd start. Notice it's 3 sig figs for the volume. And then we go ahead and introduce the molar mass of sodium chloride, which you'd have to show all your work still. The molar mass of sodium chloride is 58.44 grams per mole. So if we use the flipped version of the molar mass, 1 mole of NaCl over 58.44 grams of NaCl. Grams of NaCl cancel, we're left with moles of NaCl per milliliter of solution. Not quite there yet, not quite molarity of chloride. You don't have to do it in this order, but if this third term recognizes that you have 1 mole of chloride ion for every 1 mole of NaCl, formula units. So now we have moles of chloride ion per milliliter of solution. And we want it moles per liter of solution, so the last term is to fix that. So if we put 1,000 milliliters over 1 liter, then milliliters cancel, and we're left with moles of chloride ion per liter of solution, and that's perfect. So rounding to 3 sig figs, I get 0.205 molar chloride ion. So that's the other number we plug into our Q. Okay. Don't forget we're going to square it, right? So plugging in those values, I get 0.012, which is the molar concentration of the lead 2, times 0.205 squared, which is the molar concentration of the chloride ion. Rounded to 2 significant figures, I get 5.1 times 10 to the negative 4. And since this is larger than our K, sometimes I have to concentrate. Is it larger? Yes, it's larger. Since it's larger, a precipitate will form. And it was just this semester when I'm thinking, you know, I usually think through it with Q, or yeah, with the Q being too high, we have too much products. The products are the ionized or the dissolved species, so we're going to have, but now I'm just like, oh, if it's large, then that means precipitate will form. So I don't even think through it this time. We'll see. So precipitate will form, and that's the answer to the question. And as you might imagine, when you see one of these on a test, just to write it will form or will not form, that ain't going to cut it. That won't even get you 1 point without showing any reason why. Got a 50-50 chance. Put some blada blada between your answer and the question. Okay, so let's do another one. And I'll draw this one over here. Another beaker. This way I have 3 beakers. We have a receiving beaker and an emptying beaker, 2 emptying beakers. So from one side, we're going to add 200 with 4 sig figs milliliters of K2CrO4 AQ. The molarity is 0.350. And then from the other side, we're kind of symmetrical. We're going to have another 200 milliliters of a different material, 0.0100 molar AgNO3 AQ. And we're going to mix them together. So the questions at hand, are we going to get a precipitate of silver chromate? Or excuse me, yeah. Silver chromate. You don't know. Would it be potassium nitrate? No, that's soluble, so silver chromate. And I'm going to talk you through the second question, but I have a handout to tell you that actually the second question won't be of the type that you'll run into on your unit exam. And the problems we have coming up are only going to be extra credit. So if next to the second one you want to put EC for extra credit or something, you can. And maybe that'll be your hint that that's not the type of question I'm going to ask on the test. But I will ask the first question. So let's take a look at that. So this is the exchange reaction, a one-way arrow showing the 2 salts and showing them switching partners, making sure that you're able to balance it. Balance it for what we call charge and mass. So 2AgNO3 plus K2CrO4 goes to form 2KNO3 and Ag2CrO4. So I'm hoping you're kind of getting in the habit now that we're going to focus on that insoluble salt over here, the silver chromate. And so we need to write another thing. And that other thing actually is going to be that equilibrium. There you go. Ag2CrO4 in equilibrium with, in its solid phase, in equilibrium with 2Ag plus CrO4 2 minus. And then last but not least, let's just go ahead and knock out the KSP expression. So KSP is equal to the molar concentration of the silver ion, Ag plus squared, times the molar concentration of the chromate. And we do have a value for KSP was given in the problem. 1.1 times 10 to the minus 12. Ooh, that's pretty low. So this first part isn't bad. We need to get to the molar concentration of our silver from our silver nitrate and the molar concentration of our chromate from our potassium chromate. And then plug them in to a Q. Let's find out Q. So this is the way I did it. There's probably more than one way to skin this cat. So I first came up with moles of the chromate and then moles of the silver. So over here on the left, we had 200 mils of solution. The molarity was, sorry, I guess the next one. 200 mils of solution, converting that to liters. So 1 liter over 1,000 milliliters. That'll give us liters. And now using the molarity of the potassium chromate, I'm going to want liters to cancel, so I'm going to use the unflipped version. 0.350 moles of K2CrO4 per 1 liter of solution. So now liters of solution are left. I'm left only with moles of K2CrO4. And you might think you're done, but you wanted moles of CrO4. So how many moles of CrO4 per mole of K2CrO4? 1 to 1. Yep, that's what that last ratio is. 1 mole of CrO4 2 minus over 1 mole of K2CrO4. And that, everything will cancel except moles of everything will cancel except for moles of CrO4 2 minus. Looks like rounding to 3 significant figures. I got a nice round number, 0.0700 moles CrO4 2 minus. In a minute here, we're just going to divide those moles by the total volume, which is 400. But we'll get to that. Before we do that, let's go ahead and knock out moles of Ag+. That, of course, came from the other side. So we had 200 milliliters in that case, too. So 200 milliliters of solution over 1. Let's go ahead and convert that to liters. So we'll go 1 liter over 1,000 milliliters. And let's go ahead and introduce the molarity of our AgNO3, which is 0.0100 moles of AgNO3 per liter of solution. Now milliliters cancel, liters cancel. We're left with moles of AgNO3. The last thing we need to do is get to moles of Ag+. So how many moles of Ag+ per mole of AgNO3? It's not 2 to 1. Yep, just 1 to 1. Yep. 1 mole of Ag+ over 1 mole of AgNO3. And that should do us. Rounding to 3 significant figures again, I get 0.00200 moles of the silver ion. Whew. So now let's come up with molarity to plug into our QSP expression. So the total volume was 400 milliliters. So we're going to take those moles and divide by 400 milliliters. So for the chromate, we take the 0.0700 moles of chromate, CrO4 2 minus, divided by 400.0 milliliters. And then we need to convert the milliliters to liters. So that works if we take it times 1,000 milliliters over 1 liter. Milliliters cancel. We have moles of chromate over a liter of solution. That is molarity. Looks like 3 sig figs again. I got 0.17 molar CrO4 2 minus. So that's one of the 2 numbers we're going to plug into our Q. Like a Star Trek Q. And then for the silver ion, we're going to do similarly. We came up with 0.00200 moles of Ag+, divided by the volume of 400.0 milliliters of solution. And then we need to introduce a second term, 1,000 milliliters over 1 liter, to get milliliters to cancel, be left with units of liters in the denominator. 3 sig figs, That's our second number, 0.00500 molar Ag plus. So we're close. So we're just going to take those numbers and plug them into a QSP expression. So QSP takes or Q or QSP takes the same form as K or KSP. It's the molar concentration of the silver ion squared, Ag plus squared, times the molar concentration of the CrO4 2 minus raised to the first power. So here we go. Plugging in our numbers, I get 0.00500 squared times 0.175. And this is before precipitation occurs. And we are going to take a look at that second part. So let's see, I'm going to go ahead and say molar concentration of Ag plus. I'll go ahead and put a 0 here for initial is 0.00500 molar. The initial concentration of chromate is 0.175 molar. All right. So rounding it to 3 significant figures, I get 4.38 times 10 to the minus 6th, which is definitely higher than our KSP. So a precipitate will form. It's funny, like I said, I used to struggle with that. I'd take a few minutes, I'm like, oh, okay, well, but now I got it. How many years have I been doing this? All right, so that's it. Precipitate will form. Seems like a lot of work to come up with a yes-no, answer a yes-no question. Welcome to chemistry, I suppose. Okay, so one of those will be on the test in one way or another. Or 2 ways or another. So this is where I'm stepping off. This is question number 2. This is then the sort of question that I won't necessarily ask you. So we want to know what percent, I think it's what percent of Ag or plus is left, I think. So in order to know how much Ag plus is left, let's go see how much Ag2CrO4 precipitates. And in order to do that, we need to come to some understandings or make some assumptions. So I'm going to go ahead and draw my sludge down here. Sludge, and that is my Ag2CrO4 solid. So that means, like the slide says, this is saturated with regard to the insoluble salt. So like this says, and this is why I wrote down these numbers, your chromate is significantly higher initially than your silver, so we're going to actually think that when it does go ahead and pair up and precipitate, basically your silver is in limited amount and it's all pretty much consumed. So, but what isn't consumed is going to be in equilibrium with the leftover chromate. All right. So there's our equilibrium of interest. Okay. So the moles of the chromate that precipitated, assuming that all of the moles of the silver went ahead and came out. So this was the moles of the silver we had. We recognize that for every, because the formula for the insoluble salt is Ag2CrO4, we recognize that 2 moles of Ag will go out for every 1 mole, Ag plus will go out for every 1 mole of CrO4 2 minus. So then that means that the amount of CrO4 2 minus chromate that came out of solution was just 0.00100 moles. So we can, by difference, we take what we started with, which it's not on here, but a few slides ago, we said we started with 0.0700 moles of chromate, and from that subtract the amount that is pulled out during the precipitation, 0.00100 moles. And then, so this would be the moles of chromate remaining in solution, 0.0690 moles of chromate. So that's what's left running around. And that's in equilibrium with the silver. So now what we're going to do, and we'll do a little bit of this when we meet Monday, kind of substituting back in to the KSP expression to find the other one. So the molarity of the chromate ion would be the moles divided by the volume, having both of those solutions put in. So 0.0690 moles of CrO42 minus divided by 400.0 milliliters of solution. Correct it from milliliters to liters by introducing 1,000 milliliters over 1 liter. Rounding it to 4 sig figs. How do we pick up another sig fig? I think it should be 4 sig figs according to that. But I only got 3 here. I can live with that. The molarity after precipitation occurred of the chromate in solution is 0.173 moles per liter. Now we're going to substitute that back into the KSP expression, basically, to find out what the silver ion is. So this, what you're looking at, do you recognize this is the KSP expression? Okay, KSP is equal to molar concentration of silver ion squared, molar concentration of chromate ion raised to the first power. So at equilibrium, then we can substitute in that molar concentration of the chromate ion we just got and solve for the molar concentration of this silver ion. So we're basically rearranging the KSP expression. We know the molar concentration of chromate ion is 0.173 moles per liter. So if you take if you take the KSP 1.1 times 10 to the minus 12 divided by the molar concentration of the chromate ion, 0.173, and ultimately you have to take the square root of that because your silver ion was squared. See why you don't have to have one of these on the test? Rounding to should be 2 significant figures. And we're not even done yet. The molar concentration of the silver ion that's left in solution should be 2.5 times 10 to the minus 6th moles per liter. So we were after what percent remains in solution. So now we have molarity, right? So now we get to take the molarity and get to moles. That's left in solution. So here we go. We had 400 mils of solution, 400.0 milliliters of solution. Do I correct it for? Yep. Go ahead and convert it from milliliters into liters by introducing 1 liter over 1,000 milliliters. And then if we just stick the molarity in there, then we have moles. The molarity we came up with was 2.5 times 10 to the minus 6 moles of silver ion per liter of solution. So milliliters cancel, liters cancel, we're left with moles of silver ion, and we're close. Rounding to 2 significant figures, I get 1.0 times 10 to the minus 6 cute little moles of silver ion running around in there. So to get the percent or fraction that remains in solution, we need to compare it to what was there before precipitation. So what was there before precipitation was 0.00200 moles of silver ion. What was there after is 1.0 times 10 to the minus 6 moles. To get it from a fraction into parts per 100, we multiply by 100 or 100%. Finally, rounding to 2 significant figures, okay, the percent of silver ion that remains in solution after precipitation has occurred is 0.050%. Whew. So, skip the next problem for now. And this is this, basically. In part 6, there's ultimately 3 types of problems. We just did one of the problem we did it, we calculated Q and compared it to the K, okay, to see if a precipitate would form. If it's big, if the Q is big, then a precipitate will form. If it's less than the K, the precipitate will not form. You're responsible for that, and you're also responsible for what we're going to talk about on Monday. I want to give it a little bit of time before we talk about fractional precipitation. It's not very many slides, but I think that would be good for us. So those two, but you don't need to do what we just did with the silver ion, coming up with the 0.050%. You have to do that. All right. And this just kind of clarifies, you guys have a hard copy of this. This clarifies what I mean by what we won't do. So what we won't do is, let's see. So here we go. The second part of the second example problem, that's with the silver. No. And the one I entirely skipped. I said for now, we might look at that Monday, just depending upon kind of, if I think it'll help you, we'll work on it more. But, yeah. So, all right, so you know what that means. Dun, dun, dun. Time slides. But as I walk through these, if you want to, you can circle these two, and actually these are for extra credit. They are more like the silver one we just did. So 36 and 37 are extra credit. Did you find it?
No.
What page?
There, it's right there.
Oh, right here. 7.
Doesn't look like a normal.
Yay. Yeah, so 36 and 37 are extra credit. So, you got a noisy marker.
Sorry.
Nicole.
Sorry.
Oh, okay. Well, it's the weekend, aren't we?
It's definitely time for the weekend.
It is time. Okay, so these are what this looks like. I'll warn you, my hint slide gets really busy, so, but it's just basically what we did. Okay, so are you going to get magnesium fluoride precipitating if you take magnesium chloride hexahydrate and you add it to an already prepared solution of potassium fluoride? So I have my hints up there. The bottom line, okay? You write, and I have more hints here, but it's really busy. Like I said, I warned you. Write the exchange reaction. Write the equilibrium of the insoluble salt. Write the KSP expression. Okay, you can't go wrong. Okay, so it's not necessarily balanced. So that's what my little lines are. You need to balance that thing. It's good practice. And notice that I underlined the hexahydrate part of the magnesium chloride. So be careful. If we're interested in the magnesium cation, you're going to have to kind of massage that molarity out of it. Okay. Oh, wait a minute. So it says you can ignore these waters of hydration since you're dissolving in water. Oh, yeah. Now I remember that. You can ignore them, but you have to take into account that they're in that 22.5 milligrams sample that you weigh at. So I have to double check. This was from last year. You can ignore them because they'll just go away, but you can't ignore them in the mass of what you're weighing out. Yep, and then the second thing, I said focus on the insoluble salt, which they told you was magnesium fluoride. Write the equilibrium of that. Be careful with your coefficients. And then write the KSP expression. And then we said, go ahead and you have to see how much hints I get. Use your Chem 1 skills to get to magnesium and the fluoride ion. Yeah. So don't forget, it's not in grams, it's in milligrams too. You can do it. It will be good. Okay. Next one. Oh, almost. Oh, plug into QSP and compare to KSP. Okay. Next one is lead 2 chloride going to precipitate out if you have this particular solution of potassium chloride, this particular solution of lead-2 nitrate? Again, write your balance exchange reaction, write the solubility equilibrium of the insoluble salt and the KSP expression. Then you have to determine the molar concentration of lead-2 and the chloride ion, the things that are going to make your insoluble salt, plug them into a QSP and compare to KSP. And third one that you need to do for Monday looks like this. Will you get a precipitate in A, B, or C? My hint for A is work it like the previous problems. You have sodium chloride mixing with silver nitrate. Hopefully your kind of bells should go off. Well, what's going to be insoluble? Your choices are sodium nitrate or silver chloride and silver chloride. Because I don't think the problem says what's going to be insoluble. We did talk about general solubility rules the other day. Let's see, what else do I have? So for the second one, it gives you a tiny little volume of a particular molar concentration of the potassium bromide, and you have a saturated silver chloride solution. Will silver bromide precipitate? I'm trying to remember, do I have any more hints for that one? Yeah. So you're like, well, how would I know? All they did was told me that the solution was saturated with silver chloride. What do I know my silver ion concentration is? Well, you can look up the KSP value for silver chloride, and then you can, let's see, that was C. You can look up the silver chloride. Oh, we know how you can get the molar concentration of the silver ion from, wow, did you drive your bike? Okay, because it's raining. I think it's a brief shower. They're still bulldozing over there, so it must not be too set in. It is. Talk about mud. But do you guys know what I'm trying to say? You can get molar concentration silver ion from the solubility of
You're
the.
gone for the day, aren't you?
I am done. I am out of here. So hopefully, I hope so. And then if you look at the top there, there's C. And I said the possible precipitate is magnesium hydroxide. Oh my gosh. Okay.
That's good enough, all right.
In all problems, you can ignore. Oh, so you're dripping a little bit of solution in. Don't worry that 0.05 milliliters, what it's going to do to your 1 liter in A, or what it's going to do to your 250 milliliters in B, or to your 3 liters in C. You don't have to factor that in. Isn't that nice? Yep, just a blip. And skip/extra credit, skip/extra credit question mark. All right? So, very good.